introduce our speaker today?
Yeah, sure. So our speaker is Jaren Ashcraft from the University of Arizona. Jaren is actually doing a short-term detail here at Goddard as part of the, I never get this acronym right, NGSTRO.
Oh, I have it in the next slide. It's all
Okay.
good. It's TGRO, but yeah.
Okay, program. So that allows him to go to different NASA centers and work with researchers. And he's here working with me on some of the habitable world observatory simulations, specifically looking at polarization aberrations and how that could impact our high contrast imaging. And he is graduating and defending in, which will be successful in April, and I'm sure he is very much looking forward to that. So please take it away.
Thank you, and thank you very much for hosting me today. It's really cool to get to talk, hang out at Goddard. It's been really fun being here, and this is unfortunately my last day, but I had a lot of fun. And today I'll be talking a little bit about polarization aberrations, a topic near and dear to my heart and my game, and how they sort of set limits for high contrast imaging instruments in next generation observatories. I wanted to do a bit of an extended introduction because this is my first time here and first time meeting a lot of you. I'm originally from the Big Island of Hawaii, so how's it? And I got my bachelor's of science in optical engineering from the Institute of Optics at the University of Rochester. Right after that, I moved over to the University of Arizona, where I'm enrolled in my PhD. My advisor is Dr. Ewan Douglas over in the astronomy department, but I work a lot with Dr. Daewoo Kim in the OpSci and the Loft group there. And as Brian mentioned, I'm on the NASA Space Technology Graduate Research Opportunity that allows me to come around to NASA centers and do some research. My particular focus is on enhancing integrated and open source modeling efforts with one of the kind of key features of that is integrating polarization into our image simulations. So just to kind of back everything up to talk about high contrast imaging and all get on the same definition here. My friend once said that high contrast imaging is the science of detecting faint things next to bright things. And that can be whatever. I found this figure from Dr. Kathleen Follett in this intro to differential high contrast imaging paper that was really excellent. If you say wanted to image a piece of bioluminescent algae on a lighthouse, that would be a really hard problem because the algae is very faint and the lighthouse is very bright. In astrophysics, particularly in exoplanet detection, we're thinking on larger scales with similar contrast ratios where we're trying to image a planet orbiting a very bright star. And we talk about contrast ratio or normalized intensity, and that is very simply the ratio of the flux you detect from the faint thing to the flux you detect from the bright thing. And so when you try to achieve some contrast, you are doing high contrast imaging. And to do so, we use these instruments called coronagraphs. So this is an instrument that would sit behind a telescope that is receiving light from a distant planet and star. It goes through some AO system so that you have a nice and crisp image. And then you do what any child would do that accidentally looked at the sun, you'd kind of block it out, right? You filter the starlight by putting a focal plane mask there where the image is formed. Unfortunately, diffraction happens, and so a little bit of that starlight makes it to the final pupil plane. And so use a little undersized aperture to block the remainder of that starlight, or a lot of it. And the result is a little visible companion that you can see there on the right, which it would be the planet orbiting your star that is much fainter than the star. And this is kind of the principle of coronography. To achieve really high contrast, we use sort of these really exotic coronograph architectures with very kind of like space age names, like the phase-apodized pupil Leo coronograph and vector vortex coronograph. And so those are really cool and also help us to achieve a really, really high contrast because direct imaging is a very hard problem. This plot is from kind of a GitHub repository hosted by Vanessa Bailey that shows the flux ratio, that contrast ratio you need in order to detect an Earth-like exoplanet at 10 parsecs. That flux ratio is 1 part in 10 billion or 10 to the minus 10. So that's incredibly difficult. The lines on this plot sort of show the flux ratios capable that I believe Roman's coronagraph will be capable of. So we need to make use of these really cool coronagraphs in order to achieve these deep contrasts to find Earth-like analogs. And one key limiter of these effects can be polarization aberrations. Scott, this is your paper. Thank you very much for writing it. Polarization aberrations are sort of something that we're beginning to consider, mostly because it's a very small source of aberration. Hasn't really been a big limiter to previous missions, but in order to detect these Earth-like analogs, it's something we're needing to consider. So that's kind of what the subject of this talk is going to be about. But before getting into that, we should probably back up and talk about what exactly I mean about polarization. So again, just getting on the same page. When I say polarization, I'm talking about where light is whippling in a given direction, like this electromagnetic field. The polarization of it is the orientation of that electric field vector as it's propagating through the system. Polarization can be found in a lot of places, just kind of every day. So on the top left, you can use it to analyze stress patterns in glasses that a lot of people in this room are wearing. Thin film effects, kind of like oil slicks on roads that you may have seen, have this very cool rainbow effect that happens to be very polarized. Polarized sunglasses can help you see through ocean glint into the ocean. They form the basis of liquid crystal displays like this, little calculator display on the bottom right. And I think we can officially say back in the day now, were the basis of those real 3D movie glasses that let you kind of get this this illusion of a 3D image. Those were all polarizers. And as it turns out, polarization is very, very useful for science, especially if you're trying to do faint detection of polarized signals, like the scatter of light off of circumstellar disks. Now, this is an image from my buddy Miles Lucas. He's a graduate student, very talented at the University of Hawaii, and does some of the coolest astrophotography with the Vampires instrument at Subaru telescope. And this just kind of highlights the kind of data that you can get by leveraging polarization. So not only, I talked before about how it might be limiting to high contrast imaging, but it's also a really cool tool that is important to understand. Unfortunately, the math can get a bit much. This is just a screenshot from my graduate E&M textbook on how you compute the pointing vector. But there's a lot of terms you need to carry around. So when I talk about polarization and use it in the day-to-day, I make a couple assumptions so that we can factor out the terms that correspond to the wave-like pattern. And if you factor those out, you can actually just operate on the complex amplitudes of the waves in a given polarization state. And the result on the bottom left is this little vector of length 2 that represents, it's just like a complex number that represents the amplitude of a wave in a given polarization state. So that's much easier to deal with. And for every vector of that size, there needs to be a corresponding matrix operator, this 2x2 matrix, which we call Jones matrices. And so to do the propagation of the complex amplitude of an electromagnetic field through a polarizing optical system, it's a multiplication of a 2x2 matrix by a 2x1 vector. That's nice. And so it makes things like optical modeling really easy so that we can do sort of more nuanced modeling later down the line. Here's just kind of an example of what a horizontal polarizer looks like, that kind of thing. Just passes one of the components, doesn't pass the other one. And that's kind of how some sunglasses work. To talk in the more general case of light matter interactions, I want to point to kind of the case of light just hitting say a glass surface at a non-normal angle of incidence. So whenever light is hitting something at a non-normal angle of incidence, the interaction, generally speaking, is polarizing. And we need to track the complex amplitude coefficients of both the reflected path, the green in the top right, and the transmitted path, which is the blue in the bottom right. And we can configure a Jones matrix that contains the complex amplitude coefficients for each of these paths very simply by arranging them kind of on the diagonal. So we can describe a large variety of light matter interactions just with Jones matrices. If you were to plot these things as a function of angle of incidence, say the reflected path, this is the case for the Gemini North primary mirror coating, which is a small dielectric over a silver layer. Because the quantities are complex, we need to plot, the real imaginary, or in this case, the amplitude on the left and the phase on the right. What we see is we plotted the amplitude and phase for both polarization states. One is the dotted line, the other is the solid. And they actually differ as a function of angle of incidence in this apparently quadratic trend. So we know that essentially systems with large variation in angle of incidence will have this difference in polarization dependent performance. And hey, guess what else has a large variation in angle of incidence? All the telescopes we want. So that's, these things are great. These are the giant segmented mirror telescopes, specifically a class ground-based 30-meter telescopes. My collaborators and I have been calling them GSMTs, but they're also very commonly referred to as the ELTs. The European Extremely Large Telescope is on the bottom left. Giant Magellan Telescope is in the center. 30-meter telescope is on the right. And all of these have direct exoplanet imaging as a key science goal of theirs. So some collaborators and I were curious if polarization would be a significant effect for them. Now, we do know that they will experience an amount of polarization simply by looking at maps of the angle of incidence, and that's what's plotted on the left. We can see sort of the top row is the primary mirror angle of incidence, the middle row is the secondary mirror angle of incidence, and the bottom row is the tertiary mirror. The ELT kind of has two, so we picked one. And we can see that the sort of range of angle of incidence is, from 0 to 15 degrees on the primary and secondary. And on the tertiary, it's, in the region of 40. Plotted the regions shaded in blue on the right there, where we can see ample splitting of the different amplitudes of a given polarization state. So we know that there will be, some kind of polarization performance degradation simply because of the geometry of the system and that light can be polarized. And to do that, we need to describe polarization aberrations, and we do so using the Jones pupil. Now, this isn't any different from those 2x2 matrices I've shown before. In fact, exact same. The only thing that I've done here that's different that makes these pretty maps is you evaluate the Jones matrix for each point in an optical beam that propagates through a telescope. So every point on one of these plots represents an element of the Jones matrix. And because the matrix elements are complex, we plot the amplitude on the left and the phase on the right. And something kind of interesting comes out. If you look at the on diagonals in the phase elements, the telescopes, in this case for the TNT, have a very particular aberration that a lot of us in this room probably have, and that's astigmatism. So it looks like the GSMTs need an eye doctor, and when you need an eye doctor, you contact, you need one to like diagnose and fix the aberration in your eye. You get glasses. When telescopes have the same problem, they contact optical engineers, and so that's what we're trying to diagnose and fix. Now, in order to do this, we kind of needed a platform with which to do so. So this begins the advertisement portion of the presentation. I wrote an open source package to do this kind of polarization aberration calculation that uses Python to talk to commercial ray tracers and open source physical optics propagators. I called it Poke. We can talk about the story of that later. But I wrote an SPIE proceedings about it for optics and photonics, just this most recent one in 2023, if any of you are interested in checking out some of the features. But the main goal was to be able to very quickly and very simply do these Jones pupil simulations. So polarization ray tracing is the main kind of calculus with which you create these Jones pupils. This was a technique largely developed by Russell Chipman's lab at the University of Arizona. He taught my polarization and optical design class. I've verified it against Code 5's full grid macro, which very much does the same kind of technique, uses the coordinate system information that you get from rays, and then the kind of light matter interaction kind of effects that I had shown in the previous slide, wraps that all up in a good matrix, and then outputs the Jones pupil. It allows you to describe your spatially varying amplitude and phase aberrations purely because light can be polarized. I also wrote in a multi-layer thin film kind of calculator. This is kind of where I show off the power of doing some of this kind of thing in Python. On the left, I just gave it a random stack of alternating dielectrics, just to see what it could come up with. The reflectance is all over the place. And then I fed it to an optimizer in SciPy to see if I could create a long pass filter that passed things past 600 nanometers. And indeed, it figured it out. We can also use this in the polarization ray tracing calculations to see how multi-layer thin films on observatory mirrors, say, or dichroics, will impact the polarization dependent performance of a system. It also supports spatially varying thin films, because I was sort of interested in tolerancing how the film uniformity impacted chronographic performance. So I applied an astigmatic kind of coding. Never do this, by the way, and looked at the sort of corresponding Jones pupil simulation, and indeed the structure shows up pretty readily. So those were things I was curious about. In terms of serving as an integrated modeling tool, these are sort of the software package it officially supports, and that I use these and have like an interfaces module to talk to them directly. It supports sequential ray tracing with Zemax Optics Studio through the Python API and Synopsys' Code 5 sequential ray tracer, as well as exporting the Jones pupil as wavefront objects in Poppy and as polarized wavefront objects in HCI, which are diffraction modeling tools that I have to use a lot in my research. So I wanted to support compatibility with them in the hopes that maybe it would help someone else. But yeah, advertisement is officially over. Thank you for listening. I built this tool so that we could start doing these Jones pupil simulations for the giant segmented mirror telescopes. And so this is the Jones pupil for the extremely large telescope. This is a 30-meter telescope. and this is the Giant Magellan Telescope. And all of them kind of have those same trends. You might recognize like a similarity in the astigmatism that you see on diagonal in the phase elements. And so we sought to quantify how this actually impacted imaging. So we plugged these data into a coronagraph kind of image simulation model, that we wrote in HCI and examined the peak degradation to normalized intensity, or that contrast ratio, subject to coronagraphs of a couple different orders. Now, these are these kind of mathematical perfect coronagraph models. They can't really be built, but they tell us sort of about the spatial structure of what's being rejected. And what we see, that's what these lines here are, is the kind of peak contrast degradation as a function of wavelength. Each color of the line is a different telescope. The line style is the coronagraph kind of starlight rejection order. Is that the second and fourth coronagraph orders for all telescopes actually suffer quite greatly from polarization aberration, short of like, kind of depending on how you count J through K band, because we know 10 to the -5, 10 to the -6 is what the GSMTs are probably going to be able to get to because of the limits of their AO system. But once you get to shorter wavelengths, polarization aberrations definitely start becoming an effect, wherever the kind of peak degradation is. Once you move over to the 6th order chronographs, however, the problem gets cleaned up. So a lot of the structure of polarization aberrations that makes it through to the final focal plane can be rejected by 6th order chronographs. And so that's very cool, that there's kind of a way out that we can just use chronographs that are a little better at rejecting starlight.
Jaren, one question.
Yeah.
Can you go back one slide? So you're evaluating that contrast at a given working angle.
It's actually just the maximum. So it's not a particular given working angle.
It's the best contrast that you achieve. And then, but the 2nd, 4th, and 6th order all have different inner working angles, right?
Yeah. So they're all different working angles. It's essentially you get the resulting field to do NP dot max on that and find what the kind of worst case in the focal plane is.
I have a question too.
Yeah.
Is there I'm having a hard time intuitively understanding why there's such a big difference between 4th order and 6th order. I would expect 4th order to be maybe somewhere in between 2nd and 6th, but it's really like 2 and 4, and then 6 all the way down here. Is it possibly? Do you have any sense of why that is? Is it related to the inner working angle? Because most of the polarization aberration energies are on the IWA, so maybe 6th order having a larger working angle.
Yeah.
So
So
filter out more of that. Is that, or is there a different reason?
So I don't have a perfect understanding of how these kind of perfect chronographs work, but sort of my understanding is that they are tailored to reject a certain spatial mode given an aperture. And so the 6th order chronographs reject like 3rd order spatial modes in electric field, which are like the Seidel phase aberrations, which look like astigmatism.
Okay.
And so the phase aberrations are sort of really punishing because they cause that blurring near the inner working angle, really shaping the core of your point spread function. I don't know that that's exactly correct in terms of the mathematical construction of them, but that's how I've been thinking of them. That because the aberrations look so much like 3rd order aberrations, they're very well rejected by the 6th order chronograph. Which I think is related to larger inner working angle, right?
Yeah,
So
sense.
there's that. Any other questions on this plot? Thank you.
I have one real quick, actually. This is Tyler online. Is that when you're selecting, I mean, you said you're picking the max area. I mean, are you constraining this to the same sky separation range or lambda over D?
I think it would be closer to, it's not constrained to the same sky separation range, closer to lambda over D. It truly is just the maximum of the point spread function, like at the essentially inner working angle of these coronagraphs.
But not in projected sky angle.
Not in projected sky, no.
So that, okay, I would maybe consider plotting it that way because that's not a fair comparison in wavelength space at all.
Yeah. What is it? We do get there later in the presentation.
Okay.
To kind of an experiment like that. But this is kind of the results of the paper that we have published doing this kind of approach, just looking at how bad it can get. But you're absolutely correct. It's the fair comparison is to fix a point on sky.
Right, okay, thanks.
Thank you very much. All right, kind of unpacking that data a little bit, I just pulled out some of the point spread functions from IBAM. Each row is a different telescope, each column is one of these chronograph orders, just to kind of show you how well the sixth order chronograph is able to reject it. But just as the discussion we sort of just had, as you move towards the right in this grid, because you get better star light rejection, you actually have lesser sensitivity to resolve things very close to the star. The inner working angle is larger. And so this is a trade space that we had kind of found out about in writing this paper. So if you're checking it out, once again, another advertisement. These were the two people I primarily worked with, Dr. Rania Anche and Dr. Sebastian Haffert at the University of Arizona, as well as investigators from a bunch of different institutions. This work is sort of ongoing. So I was sort of curious, what could we do about polarization aberrations? There's, we're not really sure about how to fix them yet, and began to kind of try to brainstorm better ideas in how we would actually remedy this situation. And so I thought back to this Fresnel reflection example. Every time light hits some surface, it is a polarizing interaction. Well, multi-layer thin films are kind of a compact way of doing a bunch of these at once. So you have a bunch of polarizing interactions in, as much as a couple wavelengths of space. And so I was curious to see if they were optimizable. If you could optimize the spatially varying thickness of the observatories, subject to, given a couple low order polynomials on all of the thickness surfaces. And if we look at the Jones people of the ELT, we find that we're dominated in high contrast imaging kind of by this crosstalk term, which is the off diagonal. And we can see it's about 1% of the incoming field. After doing the spatially varying optimization, we're able to decrease the peak amplitude of that signal by about an order of magnitude, while also enhancing the throughput of the on diagonal signal. So that means more throughput in this channel and decrease influence of that crosstalk term, the incoherent part that we can't control. Now, practically speaking, this implementation is a little difficult. Yeah.
So here you're really messing with you're playing with the thicknesses and the dielectric layer content of the coating itself.
Yeah, in this case, it is just this thickness, so I'm not optimizing the refractive index. Okay. Mostly because I wasn't super sure on how to do that, really. I know that maybe you could play some games to get some low order polynomial deposition on a mirror. Certainly it'd be difficult to do it at scale of 30 meters. But yeah, so just the thickness of the film.
Do you have a map showing what the thickness is after you optimize it?
I don't have it in the slide deck now, I'm afraid, but I imposed constraints on it to basically not make it get aggressively large or too thin, essentially, to try and maintain it.
That's what I was gonna ask, what is the physical variation over the aperture that? Okay.
Yeah, as it turns out, the largest sensitivity in this case was actually just sort of the piston mode. So the constant thickness, and they were pretty small departures on top of that. But I hadn't really looked into a large sensitivity analysis of that yet either.
Thanks.
Yeah, thank you very much. So anyways, this was just kind of an exploration into, hey, maybe this is a free parameter in terms of optimizing the observatory and chronographic performance to be relatively insensitive to polarization aberrations without really messing with the chronograph at all. Another investigation that we're doing, sort of supplementary to this research, is understanding the effects of non-uniform thin film deposition. So we aren't guaranteed that the film is going to be exactly constant layer. In fact, it may spatially vary. And so using Fouquet's ability to model spatially non-uniform thin films, I tried assigning some low order focus and tilt shaped polynomials to different hexagonal segments on a 30-meter telescope primary mirror. And we know about the aluminum oxide layer that inevitably grows on that will inevitably grow on the bare aluminum giant Magellan telescope. So tried to parameterize it with this sort of power law error. The difference in the point spread function, so these data are if you took the image of the nominal point spread function and then subtracted the aberrated one with the spatially non-uniform thin films, shows a really small amount of variation in contrast. And so I tried to constrain this by doing essentially a set of Monte Carlo runs for the ELT, TMT, and GMT, all of different chronograph orders. and found that for variable thin films on all of the telescope, or on the primary mirror, specifically the segmented part of the telescope, the RMS contrast variation doesn't really exceed 10 to the minus 8. So they should be fairly insensitive to that. But more sensitive systems at comparable polarization aberration levels may be concerned. Because we're about halfway through the talk, just to kind of review the work that we have done in support of the GSMTs, we found that polarization aberrations can be a limiter with giant segmented mirror telescopes, constructed an open source platform with which to model these polarization aberrations through Poke, and like integrated modeling of ray tracers and diffraction packages, and are investigating potential strategies to compensate for polarization aberrations. The big question that I haven't really addressed yet is, hey, Jaren, why are you even here at Goddard? We did get to that earlier. I'm here to work on the influence of polarization aberrations on next generation space telescopes. Now, I may be like the most novice person in terms of the LUVOIR and HABEX missions here, so I won't go too much into them. But in both of the final reports, the optical design of LUVOIR and HABEX had constraints imposed on them to minimize polarization aberrations. So LUVOIR's optical design had a constraint on the primary to secondary mirror separation to ensure that there wasn't a maximum angle of incidence greater than 12 degrees to minimize the polarization dependent aberrations that would negatively affect coronagraph performance. HABEX approached it slightly differently, or kind of parameterized differently, by constraining the focal ratio of the primary mirror. This is how fast the mirror comes to a focus, to be f2.25 or greater. So we know that these are going to be limiters for next generation missions. And indeed, when Astro 2020 came out with the decadal survey recommending a large, stable IRO UV telescope with high contrast imaging capable of this 10 to the minus 10 normalized intensity detection, we know that we need to revisit the problem of polarization aberrations. And so that's why I'm here. I'm here to kind of reassess whether or not the 12-degree angle of incidence constraint was sufficient, and get kind of a good understanding of how the focal plane responds to changing the angle of incidence, that maximum 12-degree. If we change that maximum, how does the focal plane respond to that change? So we begin with the LUVOIR's eclipse coronagraph. This is the apodized pupil Leo coronagraph for LUVOIR A. I always thought that the apodizers kind of looked like Rorschach ink blots, so that's kind of a fun thing. But this sits at like a pupil plane or an image of the telescope's primary mirror. Light passes it, comes to a focus at a focal plane mass whose radius is 3.5 lambda over d. And then we have a rotationally symmetric simple Leo stop that tries to block some of that diffracted starlight. The modeling pipeline looks something like this, where we have a coding recipe provided to us by Manuela Luis. Thank you very much for that. In this case, we're looking at ELIF, which is a lithium fluoride over aluminum kind of coding that is a function of wavelength. We also have several kind of Code 5 telescope ray trace models, which are a function of this angle of incidence maximum. Thank you very much to Joe Howard for that. And these data are plugged into Poke. The Poke then outputs an HCI5 polarized wavefront that we can propagate through the LUVOIR A eclipse coronagraph to get a library of point spread functions that are a function of this maximum angle of incidence constraint and wavelength. And these are broadband simulations, like 10% centered on the center wavelength. So the first experiment I did, and we had kind of visited this constraint in an earlier discussion, was just take a small ring aperture right outside of the inner working angle of the focal plane with a width of like 0.5 lambda over d. And I was curious about how the mean value of that changed as you perturb wavelength and this maximum angle of incidence constraint. This plot on the right kind of shows what the results of that are. Each point on this is one of the mean values in that ring aperture. And we see kind of something that we already knew, that polarization aberrations get worse at shorter wavelengths. That blue line at 385 nanometers is kind of the worst performing, whereas the one at 1791 doesn't really change very much. The total simulation runtime was about 100 minutes to do all of these simulations, so we can brute force our way through a lot of trends very fast. But it really kind of tells us something that we've already figured out, that shorter wavelengths experience more polarization aberration. The one new thing that I think is interesting that I haven't seen before is this quadratic trend to the maximum angle of incidence as a function of essentially degradation at the inner working angle of a given coronagraph. That's a cool trend that is oddly reminiscent of those quadratic kind of splitting amplitudes that I introduced at the top of the presentation when we introduced the Fresnel coefficients.
Jared,
Yes.
why, so given that the APLC was designed to achieve 10 to the -10 outside of the inner working angle, why is the minimum on your y-axis 1.5 times 10 to the -9?
I think that could be a couple of things. One, I mean, is I guess I'm unfamiliar if the design, how to say, it could be a matter of focal plane sampling, the actual like numerical background before you apply the polarization aberrations is below that like 10 to the -10, a couple times 10 to the -11. So that could be an artifact in the simulation. This was also with the introduction of the polarization aberrations of the telescope. I don't know if that had something to do with it. I don't know if the goal was like with the polarization aberrations of the Voir A, I assume yes. So I'm not really sure, I guess.
It looks like they asymptote to that value, so if you go to a maximum angle instance of 0 degrees, they're going to be at that same
Yeah, it
value.
just kind of stays there.
And there's
Yeah,
no
that makes
polarization
sense.
aberration there.
Yeah, that would be worth revisiting. Thank you for pointing that out. But yeah, so I mean, that's kind of the current scale. I'm also sort of ignoring a lot of things like wavefront control, for example, was not applied to this simulation, just looking at the raw point spread function, so it's sort of uncorrected. That could be another reason. But just kind of wanted to highlight that quadratic trend that we see as a function of maximum angle of incidence. However, this assumes that we are only detecting the coronagraph in the inner working angle. So this goes back to the point about the plot with the PSMTs. It's not really a fair comparison. What we need to do is sort of understand how polarization aberrations impact a real detection, because the point spread function changes with wavelength. So I have at the equation on top Rayleigh's resolution criterion. It sort of changes linearly with wavelength. And plotted some of the point spread functions of the eclipse apodizer stepping through wavelength while fixing kind of an exo-Earth's position, not at any particular angular separation. And we can see as you go to longer wavelengths, you approach the PSF core, and shorter wavelengths, it's much farther. And polarization aberrations appear predominantly at PSF core. So we need to choose a candidate. And I had already put up this plot about Earth at 10 parsecs at that 100 milliarc second at an angular separation, and then fixed that on the focal plane. These kind of dashed circles on the right show what the kind of where it would line up for a coronagraph at the 384 nanometer wavelength or 720 nanometer wavelength, very close to the PSF core, or maybe in the middle of this dark zone. So we might have different abilities to sort of recover an exoplanet from those. So essentially, we're evaluating the normalized intensity degradation where that exo-Earth actually is. And so if we do that, what we find is that one, for a lot of the longer wavelengths, this exoplanet is vignetted behind focal plane mask entirely. But for these short wavelengths, 385, 500, and 600, one, the polarization aberrations at this angular separation are much smaller, more on this 10 to the -10 level. And we have a minimum at 500 nanometers that is this trade-off between strong polarization aberrations at short wavelengths and degree of separation of the exo-Earth from the inner working angle of the coronagraph, that where the PSF core is actually bleeding through to the final focal plane. And for wavelength or maximum angle of incidence shorter than 13 degrees, have a little happy zone where we meet that 1 times 10 to the -10 threshold. So the second key takeaway of this is that there is a trade between wavelength and then actual proximity to the core of the point spread function. That's important to consider. So what I just did is kind of the maybe most rudimentary exoplanet yield study you could do, if you could even call it that. While these sort of target normalized intensities are convenient to design to, they don't tell us about how they actually impact detection. We need to do a real survey of like, can you find this list of target planets, right? And so what we're hoping to do in the future is link the polarization aberration forward model to an exoplanet yield study to see how it could actually impact observations of future habitable worlds and leverage kind of astrophysical degrees of freedom to compensate for them. To wrap it all up in conclusions, the high contrast imaging is rapidly developing for the next generation of astronomical observatories, the GSMT's and Habitable Worlds Observatory. aim to, image deeper contrast, attain small angular separations, and it's going to be an exciting time for science, but we need to understand the polarization aberrations and how they may limit the performance in order to, ultimately get a sense of what we'll be able to detect. So we also need to sort of understand techniques with which we can compensate them and understand the influence of polarization on exoplanet yield so that we can maybe find aliens and if there's life out there. Thank you very much.
Thank you so much, Jaren, for the awesome talk. So we have plenty of time for questions or discussions. So if anyone online wants to ask any questions, please feel free to raise your hand, or you can also post them in chat and also open it up to the room if there's any.
So it seems like the output of these simulations, you get a better, like if you optimize for the layering on an optical, is that at odds with other aspects of the optical modeling? Like, does that reduce throughput in any?
Yeah. So I think an important thing there that I sort of naively assumed away is that like the only instrument on board isn't like the chronograph isn't the only instrument, right? As easy as that would make everything else, you need to consider the input from everything in the observatory so that you're not punishing the rest of astrophysics in order to achieve high contrast anything. So that's something that should be included in the cost function, but I did not in my study simply because I sort of didn't have access to what those constraints were. But in principle, having the optical modeling pipeline and being able to set up the optimization problem allows you to consider what trades would benefit high contrast imaging without punishing or maybe even potentially enhancing other onboard instruments as well.
But presumably, if this is its own optic, it can be put anywhere in the pupil at any pupil plane, right?
In the case of the multi-layer thin film kind of optimized things. So for the multi-layer thin films, just putting in the pupil is hard because you need the angle of incidence to attack that off diagonal term. The sort of nominally oriented, the Jones matrix for a multi-layer thin film, nominally oriented in the pupil plane is diagonal. So it's hard to influence the off diagonal terms.
So it's an image plane.
It had been suggested that this kind of procedure could be incorporated into something like the Roman HLC, and maybe optimizing for polarization aberrations that way, and then you get the angle of incidence, and that one is, I believe, also a multi-layer thin film sort of flavored thing. So image plane, it could be on an OAP, that kind of thing has large angle of incidence on it. So different options there that ultimately I haven't had to explore yet.
Just to follow up on that, is there any chance, the pickoff mirror for the chronograph field point, is that a possibility? I mean, it's a much smaller optic. I don't know where it is positioned relative.
The pickoff mirror for the chronograph's field point, is that if you have M1, M2, M3 is the pickoff mirror that feeds the chronograph?
Potentially.
Would that be something like that? Yeah, that's super inefficient.
Chronograph.
Yeah. Making it internal to the chronograph it has the least amount of sort of difference in angle of incidence, so it's not quite as strong a lever, but way less impact on the remaining emissions, and is absolutely something that you can consider.
What is the manufacturability of, changing the thickness of in a uniform, not uniform, but in a smooth fashion?
Yeah, in a smooth fashion, I truly don't know. That's something that I think the only resource I was able to find is for X-ray mirrors. This kind of someone had kind of configured the geometry of your coating chamber kind of looks like something that's sitting up here, and then your deposition gun is tilted with respect to it. So it's already spatially non-uniform, and you can play tricks to enforce uniformity on it. Doing something rotationally symmetric is a little easier than something that has a tilt mode, because you can spin it.
Yeah.
And then change the tilt angle to sort of adjust for that. But I've done very little work in modeling, and certainly not trying to actually design it. My only experience comes from undergrad. I ran a physical vapor deposition machine and was trying to quantify exactly what the spatial non-uniformity was.
Yeah,
So
in general, you want uniform couplings, so you're going against what you want, right? So I'm not sure how well you can really achieve that, to be honest.
So there's
Especially precise, I'm not entirely sure.
Aki has a question online. Aki, do you want to go ahead and unmute?
Yes, thank you, Jaren. That was very educational. Uh, okay, so I don't understand this stuff terribly well, so let me go back a bit. So in the Louvois eclipse coronagraph, we did not split the polarizations into separate polarization channels inside the coronagraph. We said, well, we'll keep it to 12 degrees and we're going to say that's good enough and we won't have to split polarizations. Habex did split the polarizations in their coronagraph. But if I understand this correctly, what you're talking about here is contrast degradation from across terms. So this splitting, am I correct in assuming that splitting the polarizations inside the coronagraph does or does not help here?
Thank you very much for your question. To kind of help clarify that, these data that I show include no sort of wavefront compensation or splitting of the coronagraphs into orthogonal polarization states. One of the big challenges, or I guess there's sort of two big challenges when you have these incoherent, differently polarized fields. Actually, let's go to a Jones pupil. Right here. This actually isn't a great example. Let's go back to the DSMPs. You can see if you look on the on diagonals of the two columns on the left, these aberrations kind of have different signs. And so this is where splitting the polarization state, splitting it into two channels helps you because you can use the deformable mirror to control the on diagonal elements. Once you have done that, the off diagonal element is something that you can't split because it is also, say, X polarized. And follows that split. And so your wavefront control routine needs to find some minimum between, in this case, say, the two plots phi xx and phi xy. I guess wrap it back to your question. Both matter, but once you have split the polarization into two channels, you then need to deal with the off diagonal term. But if you don't, you're dealing with all four of them. Does that answer your question?
Yeah, I think so. I guess I wonder how much. So in all this analysis you showed, you're showing, non-split combined light contrast curves and maps. I'm wondering how much they change if we were looking just at one polarization here.
Yeah, and that's certainly kind of the natural extension of this work is bringing it more into how you would realistically implement this, and with that comes like wavefront control simulations as well.
Because I will add that one of the key questions we would like we're not where we are with Hab worlds right now. We are not picking a chronograph. We're not picking its vector vortex charge, whatever, or APLC blah, or Pia vortex or any of those things. The optics are not, what specific little optical elements we're putting into this chronograph are not our biggest issue right now. What we really need to know is how big is the thing and how much does it weigh? And so the things that we want to know is how many channels are in the chronograph, how many focal planes, what's the way, what wavefront control system are we using? So if you could provide some information on do we have to split the polarizations or not, would be super helpful sooner rather than later. Because that's something that you could if we have to do that, that could double the mass of it. Well, maybe not double, but close to double the mass of the instrument. So that's kind of where we are right now in exploring the Hab worlds trade space. So key bulk questions like that, addressing those sooner rather than later would be super helpful.
Yeah, no, thank you very much for that, guys. I appreciate it.
Jaren,
thank you.
Manuel here. Good morning, Jaren. Can you hear me?
Yes.
I have a question. You said you started modeling with the E-lift recipe. My question is, do you include the thin ALD layer, capping layer?
No, I did not. The aluminum trifluoride layer? Is that what that
No,
means?
the E-lift has aluminum plus lithium fluoride plus, I think maybe 3 to 4 nanometer layer of MAC fluoride. It's very thin.
I didn't include that.
Yeah, it's very thin. It should not affect things that much, but it's needed to make the lithium fluoride more environmentally stable, at least for the e-lift version.
You didn't really include it.
Yeah, no, I did not include that in the coding recipe, but, you know, the influence of these, I guess on the, if you go back to the thin film equation, I believe looks something like what is it, the like sine of something proportional to the thickness of the layer, so that's going to be very close to zero.
Yeah, and it's so thin.
Yeah, and it's super, yeah, it looks like cosine on the on diagonals and a sine on the off diagonals, so it looks like an identity matrix almost, but it's important to include in the model for completeness for sure.
Yeah, it could be an interesting exercise to see the difference with or without that layer.
Yeah, for sure.
And again, you can assume something like 4 nanometers of that, 3 to 4.
Yeah, sounds good. We'll get right on that. Thank you.
Yes.
Awesome. Are there any other questions online?
Yeah, I got one. Can you hear me?
Go for it, Jeff.
Hey,
Yes.
nice work, Jaren. So on the you noticed that the phase maps coming from the telescopes I sent you were pretty aberrated. Yeah, you should probably, and the reason is because the coronagraph, one concept is to pick it off at the Cassegrain focus instead of the telescope focus, which is a 3-mirror anastigmat. So I would redo the simulation that you're showing right now, but just zero at the phase and see what happens to see if you get the contrast that you expect. So
sounds good. Yeah, the scalar wavefront error that I was completely not correcting could be a huge contributor to why this isn't at the right level.
Well, so the chronograph will have, this astigmatic beam coming into it, but it'll be corrected by follow-on optics before it gets to the deep into the chronograph, right? All the control stuff. So I would just zero it out, and then rerun it.
Question on the slide, I think it was 39, related to your thin film optimization. Yeah, can you flip back to also slide 38 before optimization? So it looks like you, as you attempted, you have reduced the energy in the off diagonal terms, but you have to pay a penalty somewhere. And it seems visually like you're actually causing the diagonal terms to become more different from each other, which, you're kind of robbing Peter to pay Paul a little bit, because I'm just wondering if you have a sense of how much you can whack down the off diagonal term before you really start to hurt from the discrepancy in the diagonal.
Yeah, I think another kind of I don't have a sense for how far you can go. One of the key areas where I noticed the degradation, and where admittedly I think this is misleading, and I apologize for that, is that this is monochromatic. It gets much worse at other wavelengths if you do this. Granted, I've also performed the optimization at multiple wavelengths to try and trade it off, but in truth, this is this good because it was just sort of this very simple one-off study conducted at a single wavelength. I did no broadband evaluation whatsoever. So that's kind of where my intuition says the payment happens. Like you can find one phase solution that works once, but as soon as you depart from that, it gets difficult. Gotcha.
Great. Any other questions in the room or online? Seeing any? All right.
Sorry,
Jaren.
one more.
Yeah, go
Wait, one
for it.
more.
Sorry,
Sorry,
go for it.
there. I'm trying to electronically raise my hand fast enough. So, all right. So getting back to one of the key questions you asked, which is a good one, was 12 degrees enough? I'm not sure what you think the answer to that is.
Yeah, I am also not sure what the answer to that is. I think this is the sort of second half of the presentation, if you will, is sort of this is what I've been spending the last 2 weeks doing, kind of setting up the hardware to do this forward modeling, and then running 2 very trivial experiments. I think with this optical modeling pipeline, we can sort of begin to add the perturbations and further constrain the model to actually arrive at an answer to that question. That's very important. And so,
I guess,
oh, sorry.
I guess one thing that needs to happen before you're ready to answer that question is, we get, I guess we need to figure out why your other plot, it was 10 to the minus 9 on the scale, not 10 to the minus 10. I guess maybe Joe said, maybe, I don't know, maybe it's part of what Joe said there about using a different, I don't know, picking off the Cassegrain or whatever, I'm not sure. But I guess I'm trying to figure out what are the steps, because this is the other thing that we want to know very soon for where we are in our architecture trade studies is how far away does the secondary have to be from the primary? So and the key question there being, and can we fit this in a rocket? So, or which rockets can we fit this thing in if the secondary, how long is the secondary? So I guess, do you have a path to answering this in the not too distant future? So,
I think that's the main point of this project, right?
Yeah,
Is to
yeah.
answer that question.
Okay.
But, Jaren's only been working on this for like 2.5 weeks now, and one of those
yeah,
weeks,
okay, fine. I got it.
we're still
Yeah.
getting like files and everything. So, I think he's setting up the hardware in order to do, and the software in order to actually answer that question.
So I have a follow-up question and a comment. The question is, does anybody know offhand, maybe Matt knows online, how the secondary mirror depends upon the angle of incidence here? Is it just linear? In other words, we increase the maximum angle of incidence by 2 degrees and we actually don't reduce the secondary mirror distance that much, or is it a stronger?
So I can quickly answer that. This is Joe. Yeah, so all of the telescopes I gave to Jaren have the same secondary mirror distance. I was just varying the angle of incidence by going off axis. But if you want to minimize the off-axis distance for an unobstructed telescope, then you're essentially pushing the secondary mirror further out. And it's linear in this regime, but it'll be nonlinear as you get closer to 0, right? You got to push it out to infinity, essentially. But we're at 12. That's the current limit. And if it can get better, then you can pull it in closer.
So to reduce it by 50%, we have to increase the angle of incidence by something like 50%.
Yeah, just draw a line up to, it would probably be, I'd have to trace that because it's slightly nonlinear.
The comment I want to make is that he's labeled this the happy zone.
Yeah.
Which I understand, like we all talk about 10 to the negative 10, and that's where we're, going to be trying to get, but there's nothing magical about this number. And it drives me bonkers a little bit that we put so much effort into hitting this one number that is just derived based upon our planet around the sun. Right.
Yeah.
And we're going to be looking at a broad range of different spectral types and distances and albedos and all this stuff, right? And if you go back to that slide you were just on, the fact that this only changes by less than a factor of 2 over the entire range of things you've investigated here, to me is crazy.
Because you're going to pay a small photon noise penalty when you do TSF subtraction.
Yeah, I don't care about factor 2 on a survey scale. No big deal. Yeah. So that's really encouraging.
I have one other comment really that's going to be discussed. It's not so much a question for you, but more something that I want to put in everybody's minds. This study will inform, as Aki mentioned, whether or not we need to split polarization channels, but it's not the only factor that determines whether or not the polarization channels need to be split. Like, one of the reasons why HABEX needed to do that was because the vector vortex chronograph is sensitive to polarization in other ways that aren't necessarily coupled to the aberrations. Although they do couple polarization aberrations, and I'm a little scared about what would happen. This is more of a comment, but I also am curious, since we're not deciding right now which chronograph will end up in which architecture Havro's chronograph will be based on. how are we considering things like the vector vortex being sensitive? Like you need to split polarizations for the vector vortex, just baseline, which has like a factor of 2 impact on the mass budget, disregarding polarization aberrations, but also possibly in combination with it.
Yes, I don't, so Aki's right, like what we care about right now is, gross parameters, but. There, to understand what those gross parameters are, you have to get down into the weeds a little bit, like what you're talking about.
Yeah.
Right? And I think, Jaren, what we would need is detailed studies showing the polarization, crosstalk and aberrations and all that sort of stuff. For a handful of, high priority coronagraphs that we're considering to then inform them. So Bertrand Medicine is organizing a meeting in a couple weeks here where we can sit down and talk about how to go from how to get some of these growth parameters based on what we already know. My guess is one of the outcomes of that meeting is going to be, well, we want to make sure that we can split polarization if we need to, so you need minimum of 2 channels. We also need any class A mission has redundancy in its primary science instrument, so I don't see a way around 2 7-stage channels, but there's no way to inform the growth parameters without considering these sorts of things.
Another question, sorry, this could go on for a while. I think this is my last one. If you're doing APLC, this basic design you've got here, APLC on axis telescope, 12 degrees maximum angle of incidence, and you split. We didn't split the polarizations in eclipse, but if you did, like, how much better does this get?
I don't have a really good intuition, particularly for this chronograph. What is it? I had gotten the forward model working last week, so I would need to play with it a little bit before really being able to answer that question.
Okay, well, thanks. I mean, I totally understand you just started. This looks great, though. Super, super useful tools and analysis. So thank you.
Very much.
Yeah, awesome. Well, I think we're gonna have to cut the conversation there, but let's thank Jaren again for an awesome talk and awesome work. Thanks to everyone for joining online and in person. Those of you who are interested, we have another hybrid exoplanet seminar